Share my screen. And then talk briefly about the exam on Friday. So the exam on Friday is going to be forces and center seeking forces, not this rotational motion with inertia and looking at the actual motion. So like our kinematic equations for rotation, none of that is going to be on the exam. That's all going to be on the final. So this week, what we're starting to look at is if things are turning, if something is rotating and it's not just this point mass that I can make go away, I need to consider how that thing turns. So one of my favorite examples is the defier of all things in the physics world, Simone Biles. When she goes up to do some of her incredible acrobatics in the air, she is capitalizing on her inertia and center of mass and all of that energy. So she, if you go back to the questions in the homework that we had for the cheetahs and the lemurs or whatever they were jumping, anything jumping, that little squat motion that you do that pushes you up into the air, well, she's capitalizing on that elasticity of her muscles pushing down and getting her going. And you could actually do the math to see just how much force she has to generate to get herself going up in the air. And then we can think about the energy involved in the actual rotation, which is something that we're going to come to after we finish doing torques and center of masses and inertias. Then we'll move into energy. Then we'll do rotational energy mixed in with all of it, which is really fun. Well, okay, so to me, it's fun. It might not be to you. But to get there, we need to back things up and see how we can look at this thing called inertia. And this inertia is just saying, how hard is it to get something to go? Remember that once something is in motion, it takes a force to stop that motion. So inertia applies to both getting something going and how hard is it to stop it. They're both going to be the same thing, right? So first, we need to look at how masses are distributed. And this was the center of mass equations that I had you doing in the earlier lectures for this week. Then we look at how those masses are distributed specific to their inertia. In inertia, then we can define for different shapes of objects. And your inertial equations will be given to you except for when you need to calculate them. So by calculating them, I mean, if we have more than one mass on a thing and it's rotating, then the total inertia for that thing is going to be the sum of all inertias on that thing. So by way of example, this first little thing I have going on here, this guy. Each one of those things has its own inertia. And that is defined by this point. Call that like a point mass, where it is the mass of that thing times the radius squared away. So when we're looking at kind of the simplified thing, we want to know how big our masses are individually, and then how far away they are from the radius squared, which is the axis of rotation, not the object itself. So for each of these things here, what would I be looking at? I have a mass here and a mass here and here and here. Now, the really nice thing about this, after doing all of this trig that we've done, is we're looking for a straight line distance. So let's call this mass like B and C, and this mass A, and this mass D. If I look at this axis of rotation, which is this guy right here, I'm only looking at where those masses are relative to that axis. So for this one here, I'm told that it's 1 meter from A to B. If it's 1 meter from A to B and C is directly below B, then it's going to be 1 meter from that axis of rotation to C as well. And then for D, its distance away is going to be that 1 meter plus that half. So I'll have 1.5 meters away that is the R. So for this example, then R for mass A, let's see, that one's going to be 0 because mass A is on the axis of rotation. For mass B, then that radius is that 1 meter. For mass C, that radius is 1 meter. And for mass D, that radius is 1.5 meters. So what do I have then? If I want to know what my inertia is, my inertia then, what this notation says, is the sum, I'm adding up all of the masses and their radius squared. So again, this mr squared, where the r is the distance from the axis of rotation, not the radius of the object, is going to be for each of the individual masses. So for this particular case, what do I have? I have mass A times radius squared, which is 0, plus mass B times radius squared. Well, we said that that's 1, so 1 squared, plus mass C times its distance away, which is 1 squared, and then plus, I ran out of room, mass D times its distance away, 1.5 squared. So I want to reiterate, if I am giving you any kind of object where we need to add up the inertias for that object, then I will give you the equation for inertia. And there's a question. Okay, no, don't apologize. Don't apologize. It is the radius is from the axis of rotation, not the radius of the object. I am rotating about this bar here. So I need just a straight line distance from the bar to the point mass. And that distance is going to be this 1 meter. It's the same as the distance to B. Does that help? No, and it is, don't feel bad about that, because it's the habit. We've been doing a lot of tricks. Everybody wants to like find like this triangle distance from A and look at a hypotenuse, and you don't need to. It is from the axis of rotation. And sometimes it is more complicated than that, and we do need to do the trig to figure out how far. But just keep in mind, we're measuring from the axis of rotation to wherever that point mass is. Are we good with that? Okay. So then I can go ahead and put in my masses. Let's see, what did I call these things? Let's just go with 1 kilogram. Yeah, we're just going to call it 1 kilogram because I didn't list what the masses are. They're all going to be the same. So then I'll have 1 times 0 squared plus 1 times 1 squared plus 1 times 1 squared plus 1 times 1.5 squared. Now, this thing doesn't have an impact. So let's see, I'm going to have 1 plus 1. So I'm at 2 plus 1.5 squared, which I haven't had enough coffee to do in my head. So the moment of inertia here is going to have units of what? Let's think about this. I have a kilogram times a meter squared. So it has kilograms meter squared as my units. And every single one of these things has those units. So I can add them together. Same units, they can be added. Let me just push my 1.5. 2.25. So I'll have 2 plus 2.25, otherwise known as 4.25. Now I'm going to have you go into breakout rooms, and we're going to see what happens if I change this axis of rotation to mass D. And then the last example with these same masses, oh, I did say 1 kilogram, okay, is what happens if we do the axis of rotation around point D. I'm sorry, C. So this is for axis of rotation around A. Then we're going to want axis of rotation around D and axis of rotation around C. I want you to go into your breakout rooms. I'm going to give you 10 minutes to do this, to do D and C together. And then what we're going to come back and talk about is we're going to double check your work and see what size of inertia we end up with and what does that actually mean for this thing. Is everyone good on what I want? Okay. Stop sharing. Oops. All right, I will see you in 10 minutes. So 11:22. So how did that go for everyone? Were you able to figure out what the inertia were for C and D?
I was confused on how to find the value for the radius between B and C when we were changing the axis to mass C.
How to find the distance?
Yes.
So if you look on the picture, it's kind of a little bit obscured. That 0.5 meters is referring to the distance from C to B. So that means that A, B, and D are all that half a meter away from the axis of rotation. Does that answer your question?
Yes, thank you.
Okay. So what values did we get? What did we get for D? If I did my axis of rotation around mass D, 2.75, perfect, perfect. And what about C? Perfect. All right, so let's talk about what this means. Let me share my screen. So we have kind of like this 4.25, so we're kind of descending in our inertia for each of these masses, which is kind of cool. So that means that at A, it is increasingly more difficult to rotate that system. It's going to take more oomph or energy to make that thing go. D is improving, but C is most definitely easier because it is a much smaller number or value than everything else. Now let's think about why that is. When you see an ice skater on a skating rink and they have their arms out and then they pull their arms in and they start spinning faster. Part of that has to do with them changing their moment of inertia. So if I pull all of my mass in and keep it really close to my axis of rotation, so for my skater, it would be like this would be my skater, and I go from having arms coming out to everything is centered around the pen itself and the pen spins. That is, I have made my inertia smaller. I've made it easier to go. So that ice skater has made it easier for he or she to spin in that circle. The closer my mass is to my axis of rotation, the easier it is to get something to rotate. And that's what we're seeing in the differences in our values. Now, what I will tell you, because this is, and perhaps to make a note for yourself, is that I can look at a moment of inertia for a cylinder rolling down a hill, or a ball rolling down a hill, or a box rolling down a hill. I can look at that, and that I'm going to need the radius of that object and the mass of that object, or whatever inertia describes how that mass is distributed around its center of rotation. When I'm looking at putting multiple masses on something, and it's something you'll see when we start doing momentum and energy, is that we can like look at how things change when I move masses around. That I am looking at each, I'm going to treat each individual person, object, thing, whatever it is that I'm adding to whatever surface is going to rotate. I'm looking at them as a point mass. So I'm just taking their mass. I don't need their inertia from the distance of axis of rotation. So when you see things like we have here on our practice today, we're just looking at the masses themselves and then how far away are they from the axis of rotation, and it's a straight line motion. So you're drawing either a straight line to the X or a straight line, I'm sorry, to the Y, or a straight line to the X, depending on how we are rotating that thing. Are we clear on that? Okay. So let's do something. We'll do these two in breakout rooms. Excuse me, 1 second. All right, there we go. So what I want you to do is first make a prediction. So we have the same masses on the right-hand side of the page distributed differently. And one is going to put the axis of rotation in the middle, so on the x-axis, and the other one is going to put it on the y-axis in the middle. So talk to your group about which one you think is going to come up with the smallest moment of inertia. So which one's going to be easier, do you think, to rotate? And then go ahead and do your calculations for your moments of inertia. And then you can come back in and we'll talk about that. Cooper. There you go. So what did we come up with there? First of all, did your prediction match what your math said? Who would like to volunteer that? Anyone? Good, good. Yes, those are the two. So why do you think that the top configuration is going to be harder to rotate than the bottom configuration? Yeah, so that is the difference in the distribution of those masses, is that if the masses are farther away from the axis of rotation, that has a huge impact on how hard it is to rotate. So the one question I ask myself is then what happens if I make my rotation, say, through the 2 kilograms or through the 3 and the 4 kilogram? What do you think? You think if changing the axis of rotation so it goes diagonally through either of those, is that going to lower or increase your moment of inertia, do you suppose? Any guesses? Emmy, do you have an idea? Any guesses? I should say not an idea. And it's totally okay to be wrong.
Sorry, can you repeat what you said?
Do you think I'm going to increase, decrease, or have no impact on my moment of inertia by either rotating at a diagonal? So say connecting the 2 2s or the 3 and the 4 together.
Would it decrease?
So my first guess was that it would decrease for the top because I have smaller masses. I'm eliminating the heavier masses, the 3 and the 4, and I'd have smaller masses some distance away. I assumed that the bottom idea of connecting the 2 and rotating the big masses would increase. And come to find out, when I did the math, it actually increased on both. And that is the dominance of that radius squared there. So for, let's see what I got. For rotating with the big masses out, I got 208. Oh, no, 364, sorry. And with the small masses was 208. So the point in that kind of mental exercise is to let your intuition kind of guide you to where you think things will go. But keep in mind, we do want to double check our predictions with our math, because that radius is so dominant that sometimes what feels like it's obvious can end up being off by a bit. But you do want to kind of predict, because if you're doing the math and you have everything super close to the axis of rotation and you're getting a larger inertia for it, then chances are you're going to want to double check your math. Does that make sense to everybody?
In your video, you had 4 meters on one side and 8 meters on the other side because this was a square. But in this one, it's 4 meters on both sides now.
Yeah,
sides
that's
now?
what I thought.
So I'm just a little bit confused if we should like always be assuming it's a square like you did in your video, or if we should be assuming that this, when we get the one measurement, it's for both.
I will be very explicit as to what the sizes are for exams. Is that what you're asking?
Okay, yeah, thank you.
You're welcome. And I apologize for making that confusing. That wasn't my intention. Are we all good? Okay. All righty. The only other thing that I would throw into there to think about is the reason that we did the center of mass first is that something will always rotate easier, have a smaller inertia when it's going about its natural center of mass. And a center of mass just gives you where something natural, I hate to use the word now 3 times, how something naturally rotates. So if I do nothing to it and just spin it into the air, it is going to rotate about its center of mass. When you are doing your homework, keep in mind with center of mass work that I can make my axes anywhere. So I can start at my 0 point anywhere. I'm going to get the correct answer no matter where I put it, because I can look at my grid and pick out that point of where the center of mass of something is. It's just whether or not how I defined where that point exists relative to some axes. So if you are working through problems and you get what appears to be a different answer than somebody else, before you assume that you're doing it wrong, make sure that you compare how you've defined your axes for rotation. Does that make sense? Okay. All right, with that, we're going to wrap up a little bit early today.